Okay, today we're gonna finally talk about derivatives, how to derive them for like finite difference derivative, how to derive them, how to use Taylor series to derive expressions for derivatives. So again, I mentioned before that in numerical methods we don't solve calculus problem, we solve algebra problems. And so we need to approximate derivatives as some algebra expression that hopefully in the limit when a grid step diminishes, it will approach the true derivative in a calculus sense. So let's say that we have a grid, one-dimensional grid and some grid points. And we're solving some one-dimensional problem and we have some differential equations that formulated for this particular problem. And we need to convert this differential equations to form that computers can solve. So we need to replace all our analytical or our calculus derivatives with some approximation of them. So we have, let's say, some grid points, xk plus 1, and they can be spaced pretty arbitrarily, not necessarily equally spaced. And let's say that we have some values of function that we're looking for, say it's velocity or temperature, some values in those points. So the question is, given the 3 points, 3 values of a function, what's derivative in a point xk is? So what's the approximation for derivative in xk? So you can approach this in various ways. First, you would think, okay, I can use definition of derivative from calculus. So, which says that definition that derivative equals to limit delta x approaching 0, delta f divided by delta x. So approximately, because we cannot reach this limit in a numerical implementation, we just say it's just delta f over some delta x. Or in our case, if it's so our derivative can be written as so now we have a problem. What's delta f in this point? You can, so actual function, we can kind of visualize it that maybe going like that, although not necessarily. It can go like, maybe goes like this. We don't really know. So we may say, okay, we can feed some polynomials through all these 3 points and then just compute derivative in this point, and that's good first start. So what kind of polynomial we can feed to these 3 points? Well, first we could just feed first order polynomial or line using pair of points, like here, for example, say points xk plus 1 and xk. So we will write that this derivative equals to fk plus 1 minus fk divided by delta xk. Let's call it k plus 1. So I will use this notation. So this one is delta xk plus 1, and this is delta xk, just to write it shorter. So it's xk minus 1 equals to delta xk. So, but on the other hand, why use only these 2 points? You can also write that your first derivative at xk equals to fk minus 1 divided by delta xk. So instead of using this line, we now use this line. And you see, even from this simple example, you can get absolutely different answer to that question. So in first case, your derivative based on this line will be negative, and derivative based on this line will be positive. And of course, in other situations, it could be the same sign, but the value could be drastically different. So which one to choose? As xk minus 1 divided by xk plus 1 minus xk minus 1. So this is kind of like weight, right weight from that point. So this interval over the whole length of interval times first derivative, the forward derivative. And plus another weight, k plus 1 minus xk divided by xk plus 1 again minus xk minus 1 times backward derivative. So this is very interesting. So we have basically weighted mean of two derivatives. Forward derivative and backward derivative. This is how we get our derivative using parabola. So it's basically weighted first order derivatives or derivatives based on line as an approximation. So now let's find second derivative. So in this case, this term will cancel. And here all we will have is 2a, regardless of value x or xk. So basically, for this parabola, the second derivative for parabola is just constant anywhere. Of course, you probably know that because it's second order polynomial. So second derivative is constant, and we derived. When we were talking about interpolation, we derived expression for a. So this is just a first derivative forward, and this is also first derivative. So it's like definition of second derivative. It's a change of derivative with respect to x. So this is derivative minus value in here, in the middle of this, minus derivative in the middle of this divided by distance between them, which is half distance between those 2 points. And this is what we have here. So it's all logical. So now we found a general expression for second derivative. And for second derivative, you see, you should have always, you cannot express second derivative, of course, using line. So you need more than 2 points. Data points to find second derivative, you need at least 3. And for first derivative, it's insufficient to have 2 points, but then you will have only first order accurate derivatives forward and backward. And more accurate derivative is basically just mean of those 2 derivatives. And that would be more accurate derivative, second order. So we have now already have some general expressions for derivative, and this one can be it's very common derivative, second one, when you talk about diffusion process. So diffusion equation has second derivatives in it. So this is if you don't have constant spacing grid. So let's write these derivatives when we have constant spacing. So delta k equals to delta k plus 1 and equals to delta. So let's consider this a relatively common case, especially in the horizontal direction. In our models, usually horizontal direction is pretty uniform. Vertical can be very high resolution near the surface. For obvious reasons, you have boundary layer, sharp gradients. But in free troposphere, you have kind of coarser grid. But this one is pretty common. Situation is very common. So then you have your first derivative, second order, equals to, if you substitute to this, just fk plus 1 minus fk minus 1 divided by 2 delta. Very simple, very symmetric. So it's, if these two intervals are the same, then it's this value minus this value. And you see there is no central value involved at all. And that's kind of interesting, and it actually has consequences. But this one is a second order accurate. So if you compare to this one, is first order. And second derivative of the minimum order of accuracy, because you need minimum 3 points, will be fk minus 1 minus 2 fk plus fk plus 1 divided by delta squared. So this is the simplest expression for the, it's of course much simpler than this, but this one only true again for when this is true, for constant grid spacing. So if you don't have constant grid spacing, you cannot write it like this. You need to write it like that. So this is nice. We all of a sudden we basically have everything for atmospheric models, because all our models have only first and second derivative. Are we done here? Can we go home now? Probably not, because this some of them, especially first derivative, this one is very commonly used in equations for diffusion. Usually that's all people use, this, or it's kind of a more accurate version for non-uniform grid like this. This is all people usually do. For the first derivative though, it's debatable that this one is sufficient. This is second order derivative. And by itself it's just derivative in space, but usually our equations also have derivative in time. On the left hand side say something is evolving, there is derivative in time, and the right hand side there is derivative in space. And if you use this formula, certain derivative in time will create unstable combination with this derivative. For example, if you use forward in time scheme, in time, so you use only current time level and future time level, and you compute this derivative like this in a current time level, and you consider transported equation when you add back some stuff with some constant velocity in certain direction. Unfortunately, this scheme would be unstable. This derivative would actually would be non-compatible with forward in time derivative, and we will talk about that later when we talk about stability or linear stability of finite difference approximations, or finite difference approximations of differential equations. So some schemes can be, combination of certain schemes can be unstable, and certain other combinations can be stable. So that's important to note. So, but anyway, so now we derive them. Can we, but this one is just one way. And of course, each time if we want a better, higher order approximation of a derivative, say third order, fourth order, and so on, we cannot constantly like do this business with fitting polynomials, because our formulas will be really kind of, it's more difficult to derive. So maybe we can come up with some kind of more, kind of easier, simpler way of deriving derivatives. Let's say you want a fourth order derivative. You need some operator for so-called hyperviscosity that to suppress some noise, filter some noise, and that's fourth order derivative. How to derive fourth order derivative given how many points you need for that? So for that we need to switch. The best method for derivation of derivatives is not polynomial fitting. The best method is to use so-called Taylor series. And now we're going to finally switch to Taylor series. Let's say some function, the function of x, and you have some function, and you're looking at some, you know the value of function is point x naught, you know all the derivatives to that function at that point, and now you're asking, if I have point nearby this x, how can I compute value or predict value function in this point if I know everything about this function in nearby point x naught? So I know value in that point, I know first derivative, second, third, whatever. And of course the answer is yes, if function is continuous and has derivatives along this line, in this interval. If it doesn't have, if it's discontinuous, then the answer is no. But usually we always assume that our functions are continuous and have all the derivatives, which is generally true in atmospheric sciences, in atmospheric models, because we don't have usually shock waves, this kind of abrupt kind of changes in density or velocity. But if you deal with, I don't know, some problem when it involves explosions and stuff like that, then you have some discontinuities, and then you have definitely some problem because of that. But here we just have nice functions. So we have our Taylor series that says that value of function at this point that we don't know equals to the value of function in the points that we do know plus derivative of that function in that point that we do know, x minus x naught divided by 1 factorial, which is just 1, plus second derivative, x minus x naught divided by 2 factorial squared, and plus so on, plus some nth derivative of x minus x naught power of n divided by n factorial, plus and so on. So that's infinite series, provided that you of course have infinite number of derivatives. Usually you don't. Like if it's normal some function, maybe just like some polynomial, for example, then it has limited number of derivatives, but other functions can be unlimited number of derivatives, like sine function has unlimited number of derivatives, exponential, any power law, power function has unlimited number of derivatives. So this is our approximation. Now, right away, we have our derivative. Like say we're interested in first derivative. So how to make first derivative? Well, from this definition, you say that, and we have, let's say now, we have value of both in point values of function in this point and this. So this is our grid point values. We know them. So we know f of x and f of x naught. So now we want to know what's derivative in x naught. So from that we have that f of x equals to f x naught plus first derivative as before. We just write it as a kind of some truncated series. So we just divide it by 1. Plus, you know, this mathematical calculus notation, this is some delta x squared O. So it's order of this term. So these terms presumably progressively become smaller and smaller and smaller. So this is some error with respect to this term, some addition. So this is truncation error. So we truncated our time series and we produced truncation error. And in calculus, of course, delta x goes to 0 and this truncation error disappears. But in our our algebra world, it doesn't. It's there. So it's there implicitly. So now we can compute our derivative. That value in f naught equals to f of x minus f of x naught divided by x minus x naught. And this is exactly our first order, and then plus, or, and because 1 delta x we divide 1 delta x by this delta x. So now it becomes first order truncation. So it used to be the second, but we divide it by delta x, it becomes first order. So now we get our forward or backward derivative. In this case, it's like forward, looks from this graph. Forward derivative and plus truncation in the order of delta x. So you see, this is first order accurate approximation of a derivative if you use only 2 grid points. And same way, now how you can derive higher order first order derivative? Well, you need to preserve, you need to truncate it later for other terms. So basically what you do, you need to come up with some expression that this term will be cancelled and only third derivative term and further would remain. In that case, your truncation error automatically will decrease. So it becomes delta x of, say, cube of higher order. The higher this order, the smaller error is. Because presumably delta x is a small number. When you take small number and you take power of it, it becomes smaller and smaller and smaller. So, so we need to come up with some derivatives that cancel this term. How we do that? Well, we say, okay, so we now write it the following way. So we now need another grid point, obviously. We need to make some other point. Let's say this one is x1 and this point is x minus 1. So it's 0, x1, x minus 1. So we know this expression for x1, it's equal to fx naught plus our derivative that we want. And here x minus x1 minus x naught plus second derivative x minus x naught, x1 minus x naught squared divided by 2 plus o delta x cubed. This first equation. Second, we need to write for point x minus 1, it's equals to fx naught again. Now, this one should be x minus x naught. So our x becomes x minus 1. So it becomes minus, still the same derivative because this derivative is x naught. But this guy becomes x naught minus x1, and here is minus sign here, so that we keep this guy positive. And here it doesn't matter because it's square, so we still have the same term, but here we have, instead of x1, we have x naught minus x1 divided by 2, and this guy is squared, plus o delta x cubed. And this O delta x cubed can be different, but the order is about the same. So that's why we still call it, we write it kind of wrap everything in a under this rag and just keep all unknown term there. So now we can actually by dividing, we now need to cancel this term. How we do that? Well, we can divide this whole equation by this guy, and this whole equation by this guy, and then subtract them. And that way you cancel these terms, and you will have one equation for this derivative. And this time it's going to involve 3 grid points, x1, x naught, and x minus 1. And because this term is eliminated, it means that this truncation error is now, when divided by delta, by this one squared. And when you do all said and done, it actually will improve by 1. So it's going to be second order derivative. And actually, if you do this exercise, and I'm not going to do it, you will come up with exactly the same formulas that we did using parabola for our derivative in the center. It's exactly the same first order derivative. This is how you do this. And then, for example, you want the higher order approximation. What you do for that? Then you need to cancel another term. For that, you need actually you need to add 1 point, so that you could write instead of writing 2 equations, you write 3 equations like this, and then you will cancel second derivative first, and then you cancel third derivatives, and you will preserve delta x to the 4th power as your truncation error. So each time you add additional point, you keep improving accuracy of your derivative. So that's kind of general rule. So this one is a little bit a tedious process, of course, but actually you can write it in a matrix form and then use matrix to compute those coefficients. And let's say if you use, unfortunately there is no other way, if you use irregular grid or grid with different grid spacing, you need to pre-compute those coefficients before you run your model, and then use those coefficients for approximation of your derivatives. And you need to compute each set. These coefficients are going to be different in each particular grid point because grid spacing is all different. But let's consider this kind of simple case when grid spacing is constant. And in that case, you're actually able to derive analytical expression that would allow you to build very simple matrices that can be easily inverted even by hand, just by elimination process. So you don't really need computer to invert, at least for say up to five grid points. You can find very nice approximations for derivatives just on a piece of paper. So let's talk about that. This kind of simple case or kind of case when your grid spacing is constant, it greatly simplifies everything. So let's talk about that now. Okay, so let's consider this case when the derivatives are approximated using uniform grid. So we have uniform grid, so that delta k equals just delta constant. So we have our grid points equally spaced, k plus 1, k plus 2, k minus 1, k minus 2. So let's say that we look for derivative in this point. So we put this flag in this point, given some arbitrary number of grid points around. So let's now apply our Taylor series. So the value at some point k plus m, where m can be just departure from k, so in this case m's are like -2, -1, 0, 1, 2. So value in that point equals to value of point k plus derivative in k times m delta x divided by 1 factorial plus second derivative in k m delta x squared divided by 2 factorial plus so on, plus f some n derivative in k m delta x in the power of n over n factorial plus so on. So plus some or of delta x to the power of n plus 1. So this all other terms of this truncation of delta x n plus 1 and smaller terms. So this is our general kind of Taylor series statement in this case. So now we seek for some nth derivative in the point of k in the following form, as some sum from m equals to minus m1 to some m2, depends how many points we use here, some coefficients a m times f k plus m, so combination of those values of function in those points. And to make it kind of little bit easier expressions, we normalize it by, like, for nth derivative, you know, this reciprocal of this term, except for m, because m cannot be taken out of some summation sign. So we multiply by n factorial divided by delta x to the power of n. So this is our general form of nth derivative. It's just linear combination of values of function in those grid points. So now we just take and substitute this into this. So we have that derivative of power of n in point k equals to n factorial divided by delta x in power of n, sum, just write here m, a m times, now we substitute f k plus first derivative in k m delta x divided by 1 factorial plus second derivative m delta x squared divided by 2 factorial plus so on, plus our nth derivative, that's what we want, k m delta x cube, I mean power of n divided by n factorial plus o delta x n plus 1. So we just substituted. Now we need to cancel all terms that, so we seek for derivative. So all these terms, this term, this term, these terms, up to this term should cancel. The other, of course, will remain and will be part of our truncation error. So which means that to cancel this term, your condition for that is that sum of m a m of fk, so linear combination of values of function, should be equal to 0. Second condition, sum of m a m times, so we need to cancel this term, and delta x is a constant, so it can be taken outside because we equal it to 0, it doesn't matter. It's times m equals to 0. Next condition, sum of m a m m square sum equals to 0, and so on. So finally we get like sum of m a m m to power of n equals to, and because we use this definition here, so it's equals to 1. So that's the only one we get in front of our derivative that we want. And of course, we can actually keep going like that if you have more grid points. We have like condition m of a m m to the power n plus 1, but it's always equals to 0, all others. So we can use more and more points, and by doing so, we push this truncation error into smaller and smaller numbers. So this order of truncation error becomes bigger and bigger and bigger, so truncation becomes smaller and smaller. So it becomes more and more accurate. But we, of course, need to stop somewhere. So minimum, at least, we need this condition, reach this condition to represent nth derivative. So minimum, we should have how many equations? N plus 1. So we have derivative of n. To represent it, we need a number of coefficients a should be equals to n plus 1. So minimum number of equations, it's equal, of course, to solve this linear set of equations. This is linear set with respect to unknown coefficients a, m. We need n plus 1 equations. So for derivative of n order in k, one needs at least n plus 1 grid points. Of course, you can use more grid points, but then this is minimum that is required. If you use more grid points, it means that your truncation error will become smaller and smaller and smaller. But to represent, you need n plus 1. So for example, for first derivative n equal to 1, you need 2 grid points, and we saw that, right? You fit a line to those. For second derivative, for diffusion equation, you need at least n plus 1, 3 grid points, and so on. But for you can use 5 grid points for second derivative, but then you will have kind of more. For 5 grid points, you need 6 equations and 6 unknowns. So this is basically the method. So when we actually, for example, want first derivative, this is the same things. It just now for m, for this equation, instead of 0, it's going to be 1 here, and all others will be zeros. If you want very high accuracy for your first derivative, you can use as many points as you want, and your truncation error will keep decreasing as a result. So you will approach closer and closer to true calculus variables. The more grid points you use, the theoretically it's more and more accurate. And so this provides very simple way of deriving expressions for derivatives in this form. So just linear combination of values of function in these grid points for any derivative of any order. Just again, for nth derivative, you need n plus 1 grid points. That's basically minimum required number of grid points. So if you want a fourth derivative for hyperviscosity, you need at least 5 grid points for that to represent it on a grid. Not 3, you cannot do it with 3, only 5. Minimum. Or you can use 6, 7, 8, the more the better, but of course that would that would make it more accurate, but it would require more wider stencil for your computation, this width of grid to compute derivative. And sometimes it's not desirable because, especially on parallel computers, if you have subdomains and domains should exchange boundary information, the wider your stencil, the more data the processor should exchange with each other. And so the slower the process will be. And also computationally, you need to multiply and add more numbers. So your computational efficiency with high and high order of derivative, the high and high truncation error with small and small truncation error, you need more and more points, so you need more and more multiplication and addition, so it's going to be less efficient. So it needs to be some compromise. You need to stop somewhere. But generally, the higher order of derivative you use, especially for first derivative, the better. The more accurate it is. And let's consider some examples how you use this method to derive derivative expressions. We want first derivative, and so we want f prime in k, and we have only 2 grid points. So we have 2 points, n plus 1 equals to 2. So this is minimum required. Because it's n equal to first derivative plus 1, you need 2 grid points. And that would be minimum number of grid points that you can use to approximate first derivative. And this is what we did with our forward or backward derivative. So let's use this method. So we basically use the following equation. So first equation says that sum from, say we have fk and fk plus 1. And distance delta x. So we have the following. Sum from 0 or from m equals to 0 to m equals to 1, a m equals to 0. That's your first equation. Second equation, we right away, because it's only you have only 2 grid points, we have another one that now m, which is in m times am equals to 1. This is first derivative. So for this m in first power, this sum of these coefficients times this m should be equal to 1. So that's it. We have only 2. So if we write it as an expression, it means that a0 plus a1 equals to 0, and m, which is 0, so nothing. Then we have a1 equals to 1, from this equation a0 equals to minus 1. So our first derivative fk can be written as our n factorial, which is in this case n equal to 1, so it's 1, divided by delta x in power of 1, so delta x. And here you have these coefficients, so f0, which is fk, it's a0, it's minus 1. So we just write it's fk plus 1 minus fk divided divided by delta x already written. So it's exactly the same expression that we did that we found for the first derivative. So so now let's say, okay, this is the minimum accuracy. So we have truncation error generally, as truncation error is n power of equation or number of equations that we use, minus 1. You can actually check that. So we have 2 equations, so minus 1 is first. So truncation error, it's O of delta x first power. So this is first order derivative. So now let's have another example. What we wanna first derivative, but this time we're gonna use 3 grid points. So we have fk minus 1, fk plus 1. So let's use our rules. It means that a1 plus a2 plus a3, or not a1, it's minus, so this one is minus 1, 0, 1. So it's minus 1, 0, this is 1, equals to 0. Now our derivative guy, so m equal to 1, it's first derivative. So m, it's minus 1 times a minus 1. So this one is sum of a, this is sum of ma, plus m equal to 0 for this point, so we skip it, a0 is not here, plus a1, so this is m, it's 1, so it's plus a1 equals to 1, because that's the derivative that we want. And now we have third equation, which is m squared a, this is high accuracy now, So it's m squared. So this minus 1 squared is still 1. So 1, a minus 1. M equal to 0, still 0. I mean, 0 squared is still 0, so there is still no a naught. And then we have a1, so m equals to 1 squared is still 1, but equals to 0, not 1. So now we have 3 equations and 3 unknowns. By the way, this is the rule that you can always check your final expression. If you derive some expression for derivatives, take those coefficients and the sum should be equal to 0. If it's not, then you did some mistake somewhere. So if you solve this equation, and it's very easy to do it by elimination, you like substitute, and this is very simple equation. To do it by hand, you don't need any matrix solver. You will find that a minus 1 equals to minus 1/2, a0 equals to 0, and a1 equals to 1/2, from which you will derive the first derivative equals to fk plus 1 minus fk minus 1 divided by 2 delta x. The one that we derived before for the case using parabola, for the case when grid spacing was constant. So this is an example for first derivative and truncation error is going to be delta x squared. So this is second order truncation, second order accurate scheme. I heard in terms of truncation, I forgot to mention what it actually means. Is it just what truncation means? Is it good to have second order? Why is it good to have second order? Unlike say have truncation of first order. It's good not just because it's good because it's high number. The reason is that truncation error, you see, if it's second order, it will decrease by a factor of 4 if your grid spacing is decreased by a factor of 2. So you make your grid spacing twice as small, and your truncation error, or your error general of your numerical methods, will reduce by a factor of 4. While for first order derivative, your truncation error reduced by your truncation error will reduce the same rate as you increase your grid resolution, which is not good. You want for something better, like if your computers become twice as fast, you want to, if you use second order accurate schemes, at least you will improve your approach to calculus from algebra by much faster rate than you increase in your computing power. So you see, that's why it's very beneficial to use higher order derivatives. But it's not only the only reason. Sometimes just your solution would look it may look as that complete garbage if it's first order derivative, and we'll talk about that when we talk about approximation of differential equations. Look completely unrealistic than solution that you obtain, say, with third or second or third or even fourth order, first order accurate derivatives. Again, this one is accuracy is not order of derivative itself. This one is how accurate. This expression will improve if your grid spacing is decreased by a factor of 2. It will improve 4 times. It will become 4 times more accurate. While previous expression for the forward derivative will only the error will reduce at about the same rate as decrease in your grid spacing. Okay, so now let's another example just to make it. So we have now the same 3 grid points, and this is minimum number of points you need to approximate nth order derivative again. So for first order derivative, it's n plus 1 equal to 2, so you need 2 at least, or more. If you have more grid points, you have higher accuracy. But for second derivative, you need n equal to 2, at least 3 grid points to get any derivative at all. And of course, if you have more grid points, you will have higher order accurate derivative. So now let's derive second order derivative. So for that second order, you have again a minus 1 plus a0 plus a1 equals to 0. So it's the same as before. Now you have this m. So this is sum of a, sum of ma. So this is your function. This is first derivative. This is second derivatives. So we have minus a minus 1 plus a. This one is gone because m equal to 0 for that. Plus a 1 equals to 0. Now this one is m squared, so it's a minus 1 plus a1. But this time, unlike our previous case for the first derivative, we're talking about second derivative, so we should make this equation equals to 1. So you see, it's exactly the same matrix, this one, as for our first derivative, center differences, but right-hand side is slightly different. We used to have here 1, 0, and here we have 0 and 1. It completely changes everything. And if you solve for these coefficients, you will find that your a minus 1 equals to 1/2, a0 equals to minus 1, and a1 equals to also 1/2. So that your second derivative, k, equals to fk minus 1 minus 2fk plus fk plus 1 divided by delta squared and plus O of delta x squared. So second derivative automatically, even the smallest resolution one, has second order accurate truncation because it's second derivative actually. It's automatically because the next term after second derivative in Taylor series is the third order truncation. So this is minimum truncation. So second order derivatives always better converge on if you increase grid spacing than first order derivatives. So you really need to worry about first order derivatives the most rather than second order derivatives. Second order derivatives, they already kind of highly accurate because of this delta x square. It's not very accurate, but at least it's better than first order truncation. So this is very common expression, as I mentioned before, for diffusion equation, and central differences for first derivative are very common in, say, in advection equations, although they have some undesirable properties that we'll talk about later. So this is so let's because sometimes it's very confusing for the first time when you see this. Let's say that you want to derive fourth order derivative. Fourth order derivative. So how many grid points we need for fourth order derivative? Minimum number. It's 4, fourth order. So minimum number of grid points we need for fourth order derivative is 4 plus 1. So 5 grid points. So let's make it symmetrical. We can make it asymmetrical, but symmetrical actually would be more accurate. Now we have this, and we're looking for fourth order derivative. This derivative in k. How we express it? Again, let's write it. So our ace, it becomes basically like automatic process. So what you have here? You have for f. So it's sum. It's so you have now minus 2, minus 1, 0, 1, 2. This is your m's. So you have a minus 2 plus a minus 1 plus a0 plus a1 plus a2 equals to 0. That's always like that. First derivative terms, they come with m a. So you need to multiply. So here m is minus 2. So minus 2a minus 2 minus a minus 1. This one is 0 plus a1 plus 2a2 equals 2. And we don't want first derivative. So if you wanted first derivative using 5 grid points, this is where we would make it 1 here. But we don't want first derivative. We want fourth derivative. So here it's 0. So second derivative, m squared a, it's minus 3 squared. So it becomes 9. 9. A minus 2 minus 1. Squared is still 1. So it's, sorry, this one should be plus. No, this one is m. Yeah, it's minus. Correct. But here is plus, because minus 1 squared is still plus. Minus 1 plus a1 plus 9 a2 equals to still 0. Third derivative, it's m cubed a. So you need to cube now. So 2 cube, sorry. Yeah, my arithmetics are suffering. It's of course minus 4. It's 2 squared is 4, not 9. So now we have 3, now it's 9. So actually it's cube. So we have 8, right? No, here it should be plus, I'm sorry, because it's squared, right? Yes. So cube, it's minus 2 cube, it's minus 8. A minus 2 minus 1 cube is minus 1. So it's minus a minus 1 plus a1 plus 8 a2 equals still 0, because this is not our fourth. And finally, our fourth derivative is m fourth a. We'll have minus 2 to the power of 4, that's 16 with plus. Plus still 1 plus a1 plus 16 a2 and equals 1, because we want derivative this one. Well, this one is a little bit tedious too, but actually you still can do it like by adding, subtracting, eliminating. You can derive the coefficients, and if you derive them you will get certain coefficients, and so that you will get, if we after substitution, that your fourth derivative k equals 2, and here we will have, remember, n factorial, which is in this case is 4. So 4 factorial is like it's 3 factorial is 6, so times 4, 24, and then you will have some denominator, and I will cancel that, so that's why I won't write it like this, but I just write the final result. So of fk minus 2 minus 4 fk minus 1 plus 6 fk minus 4 fk plus 1 and plus fk plus 2 divided by delta x to the power of 4, and truncation error is O delta x squared. So because we divide by this large power and it's symmetrical, truncation error in Taylor series will be of 6th order, because 5th order will cancel out because it's symmetrical. And the 6th order divided by 4 is going to be 2nd order. So this is 2nd order accurate only scheme for the fourth derivative. But you see it involves all 5 grid points. And this is minimum fourth order derivative for this pattern when you have central point surrounded by 2 points. You can derive fourth order derivative using the same method, but putting your flag in here, then using all these points, and then that would change your m's. So here is going to be 0, minus 1, minus 2, minus 3, minus 4, and then you do the same thing, and then there's going to be different expression. But it will be probably less accurate. It's going to be delta x instead of delta x2, because it's not symmetrical. Okay, so that's I think very cool method of deriving derivatives of any order. But this is all very simple like this, only when you have constant grid spacing. Of course, you can generalize, but then you will have matrix that doesn't have only this simple A's, but also combination of some grid steps divided by grid steps. So you will have, but in general, you can write this matrix and then invert it on a computer using LaTeX library. But then you will have different set of coefficients, these A coefficients for each grid point, because all these distances will be different. So for each of these grid points, you will have to find its own set of coefficients to produce derivative in this grid point using values of function in these points. But this is, in principle, you just can do it once at the beginning of your run, and then you just on each time step you just use the same coefficients, because provided that your grid points don't move. But what if you have some method, your grid is actually changing, say some dynamically adjusting and dynamically increasing resolution in certain places, then you will have to recompute those coefficients on each grid step. So that's why it's very important to use some fast matrix inversion algorithm, like for example LaTeX in this case, because you would need to actually solve the systems of linear equations in each grid point on each time step, and it can be a very expensive process. And so that's why you always try to avoid very high order accurate derivatives, because they're expensive. You have many numbers like that. And so probably it should be some plausible compromise. For example, for second derivative, like for diffusion equation, I think in most cases this kind of second order accurate using 3 grid points pattern that we discussed before is sufficient in most cases. For first order derivatives though, it's first order differences definitely shouldn't be used in atmospheric science, except for certain cases when you really, and we will talk about that later, when we can actually improve solution using first order derivatives, just using them as an iterative process. So kind of predictor character kind of schemes. But generally, you use at least second order, third order, maybe fourth order for your first order accurate, or with truncation error of delta x to the fourth order, or second order or third order for first derivatives, because it's very important for, say, advection problem. And advection will look completely different sometimes, especially when you don't use very high resolution grid, depending on order of first derivatives that you use in your advection equation. Of course, when you have very high resolution, it doesn't really becomes less and less important. But because we never have enough resolution. Usually, when we have high resolution, it doesn't mean that now we can solve kind of problems that we couldn't solve before. What we do usually with that, when we have bigger computers, we increase domain size, and we still have the same kind of slow problem as before. This is how we actually operate. Faster computers don't mean that our computations become faster. It still takes a long time, because now we just basically do bigger domain problems. And ultimately, of course, the biggest domain is Earth, and then we stop there and then just increase resolution, and this is what global models do. Okay, so that's it for today's lecture. See you next time. Thanks.